We are looking at chapter number 8, which is gravitation. We'll be discussing the salient points of this gravitation. So, every object in the universe attracts every other object with a force, and this force is called the force of gravitation. So, gravitation, as we see that there are certain classes of interaction which we found in nature. So, gravitation is one of these, and these classes of interaction are gravitational force, electromagnetic force, the strong nuclear force, we also call it as hadronic force, and the weak nuclear forces. Newton's law of gravitation. The force, which is the gravitational force, this is an attraction force, and this acts between two bodies, two masses, m1 and m2, which are separated by a certain distance. We call it as r. So the gravitational force acting between two point objects is proportional to the product of their masses. That is, this force is directly proportional to the product of the two masses which are attracting. This is directly proportional to them and inversely proportional to the square of the radius, or you can say square of the distance between them. This r is the distance between these two particles. In this case, this is mass m1, this is mass m2. So there is a distance of r between them. So F is directly proportional to m1, m2, inversely proportional to the square of radius. When we remove this proportionality sign, then we have this capital G, which is called as the universal gravitational constant. The value of G is 6.67 into 10 to the power minus 11 Newton meter square per kg square, and this will remain, this is a constant, so it will remain same throughout our universe and in our calculations also. This G, gravitational constant, or universal gravitational constant, is independent of the nature and the size of the bodies. Also, the nature of medium between these two. This can be anywhere. This G remains same. The dimensional formula of this G is m minus 1, L 3, and T minus 2. There are certain important points we need to know about the gravitation force. This gravitation force is a central, means if we take Earth, the gravitation always acts towards this center. Also, it is a conservative force. This is the weakest force in nature. If you compare it with the electrostatic force, it is 10 to the power 36 times smaller. It is 10 to the power 18 times smaller than the nuclear force. That is why it is the weakest force. The law of gravitation is applicable to all the bodies. They can have any size, shape, or position. The sun, which we for Earth is the ultimate source of energy. The gravitational force acting between the sun and the planet. This gravitational force is responsible for the orbital motion as it provides the centripetal force. So if this is sun, and all the planets we know, they are revolving around it. How they are revolving means from where they are getting the energy, from which force. It is the centripetal force, this one. So gravitational pull of the Earth, this is known as the gravity. When we talk about if this planet is Earth, this is sun, then we call it as the gravitational pull of the Earth. Earth, by virtue of its inner mass, it attracts the bodies, and this is known as the gravitational pull. Also, the Newton's third law of motion, this also holds good for the force of gravitation, because eventually it is a force. This is going to mean that the gravitational force between two bodies are action-reaction pairs. There are certain points again for the gravitational force, it is independent of the medium between the particles. If you talk about electrostatic force, this force is dependent on the medium between the particles. The gravitational force is conservative in nature, and it expresses the force between two point mass, because we are talking about some negligible volume. But for external points of this spherical body, the whole mass can be assumed to be concentrated. If you have like this, you can assume it to be concentrated at center of mass. Acceleration due to gravity, small g. We'll come across this g very often in various calculations. So the uniform acceleration produced in a freely falling object due to gravitational pull of the earth is known as acceleration due to gravity. If this is earth, some body is being dropped, then the acceleration of this body, or the acceleration which this body feels, is the A, which is equivalent to g, that is gravity. We denote it by g, and the unit, because it is an acceleration, it is meter per second square. It has direction, so it has a vector quantity, it has a direction, and the direction is towards the center of the earth. This value of g is independent of the mass of the object, which is falling freely under gravity. This g changes very slightly from place to place, and for the calculation purposes, we take it somewhere 10 in order to simplify our calculation, but the standard value is 9.8 meter per second square. This value of acceleration due to gravity on the moon is 1/6 of the g of the earth. And if you talk about sun, it is 27 times g gravity on the earth. If you talk about the planets, we know the acceleration due to gravity is minimum on the Mercury. There is a relationship between gravity and acceleration. G is given by gm by r square, and this m is the mass of the earth, which is 6 into 10 to the power 24 kg. This r is the radius of the earth. Generally, we take it as 6400 km, and the value can be taken as 6.38 in terms of meter, 6.38 into 10 to the power 6 meter. The acceleration due to gravity at certain height h, means at certain height h from the surface of the earth, is given by this gh, g into m by r plus h square. One more expression is there, g 1 minus 2h by r. What are the factors which are going to affect the gravity? First is the shape of earth. See, this g is directly proportional to 1 by r square, as we have known this. Earth is not a proper, you can say, sphere. It is elliptical in shape, and the crust is also not very smooth, the earth crust. So the diameter at poles from this point to this point is 42 kilometers less than the diameter at equator. So if this is x, this is this, from this point to this point, it is x minus 42. So when we have less distance, because from the center of earth the distance is less, the g is minimum at equator, but it will be maximum at poles. That means if you take an object, throw from some height, the gravity will be higher at equator as compared to the gravity at pole will be higher as compared to at equator, because the poles are nearer to the center of the earth. Then rotation of earth about its own axis. If you take omega as the angular velocity of rotation of earth about its axis, we know that the earth rotates about its axis also. So the acceleration due to gravity at a place having a latitude, say lambda, is given by g dash is g minus r omega square cos square lambda. This is the angle lambda. If you take any point on the earth, like this point, okay, this is also moving. Here we have this center one. We have axis. So from this point to this point, this is the lambda, this angle we are talking about. So if you take any object here, it has some weight, say mg, and always mg is to the center of the earth. So we have to join these two. This is also lambda, and this is how it is moving with omega. The earth is rotating about its axis. So this is the formula we need to know. When we go to the pole, this angle becomes this one, lambda. Lambda becomes 90 degrees. So we put lambda equal to 90 degrees. We get g dash equal to g. So there is no effect of rotation of earth about its axis at poles, because we are talking about the point on the axis itself. But when we come to equator, this lambda becomes 0 because we are talking about this. The object is here. So the angle which it is making, lambda, becomes 0. So when we put lambda equal to 0, cos 0 is 1. So g dash will become g minus r omega squared. So g is minimum at the equator, and if earth, its rotation about its own axis, g will remain unchanged at poles. But because we see here at poles it is g dash equal to g, but at the equator and from the pole to the equator it is going to change with respect to, because the radius will remain same, with respect to the r omega square. Omega is the angular velocity by which the earth is rotating about its own axis. Then we have effect of altitude. If we have a body, say here, the h distance, and a body here at h dash distance. So what do you think that which of these body will experience more gravity? The value of g at height h from earth's surface, from this surface, is given by g dash equal to g by 1 plus h by r whole square. So by this scenario, the g increases with the decreasing altitude. That is, g decreases with the altitude. This is going to feel more gravity than this one. Then we have effect of depth. As you know, that the value of g at, say, some depth h, some h from earth's surface is given by g dash equal to g1 minus h by r. So with this case, the g will decrease with depth from the earth's surface. We are talking about now not at the height, but from here, surface. This is the center of the earth. So if you reach the center, the gravity will become 0. See, put h equal to r here. H and r will become equal. 1 minus 1 is 0. So g into 0 will be 0. So g dash will be 0. So at this point it will be 0. So g will decrease from this point to this point, say from 9.8 to some, say 9.8 is here at the earth crust. At 0, it will decrease till it reaches the center of the earth. Then we have intensity of gravitational field, say at this is very important, intensity. We write it as Eg or I. This is the intensity of gravitational field, say at some distance r from a body of mass m. So this gravitational field or intensity is given by g into m. This m capital is the mass of the earth in this case, in this example, divided by the distance of that object from the center of the earth. This is a vector quantity and the direction is towards the center of gravity of the body. So this is the scenario here. The SI unit is Newton meter and the dimensional formula is Lt to the power minus 2. The gravitational mass mg and sub g is defined by the Newton law of gravitation. Always the mass is computed because we know that this is force equal to mass into gravity. Force, how to find the mass? It will be F by G. This is the kiloweight, that is the weight of the body, and this is the acceleration due to gravity. This is how we compute the gravitational mass. Then we have gravitational potential. So what is the gravitational potential? Gravitational potential at any point in a gravitational field. See, if this is some body, Earth, say Earth, it has some gravitational field here. So gravitational potential at any point, see this point, in gravitational field, because it is in the gravitational field, this body is at the gravitational field of the body. This is equal to the work done per unit mass. So work done per unit mass in bringing a very light body from infinity to that point. So it is, say it is at infinity. It is coming at, say, some point in the gravitational field. This is denoted by Vg. Vg is given by W by N, which is eventually minus G into M by R. The SI unit is joule per kg, and it is a scalar quantity. The dimensions are L to the power 3, R to the power minus 2. Here the W is this is the work, and this is negative. That means gravitational potential is always negative. Always negative. This sign shows that. Gravitational potential energy. So now we have seen about the gravitational potential. What is gravitational potential energy? So gravitational potential energy of any object at any point is gravitational field in the gravitational field, because every body has some gravitational pull. Say again, we take the example of Earth. So gravitational potential of any object at any point in the gravitational field is equal to the work done bringing it from infinity to that point, and this is denoted by V. And this gravitational potential energy is given by minus G into capital L, small m by R. This capital M in this case is Earth. This m is the body's mass. Again, we have a negative sign. This shows that the gravitational potential energy decreases with the increase in the distance. The gravitational potential energy at, say, certain height h from the surface of the Earth is given by minus G into capital M small m by R plus h, which is mg capital R by 1 plus h by R. We just have divided them or rearranged them. Satellite. We have man-made satellite, we have natural satellite. So a heavenly object which is revolving around a planet is called a satellite. So if we have sun, we can say that Earth is a satellite. Moon is a satellite of Earth because moon goes around Earth. Earth goes around sun. So natural satellites are those heavenly objects which are not man-made. We haven't made them. They revolve around the Earth like this. But artificial satellites are those objects which are man-made and they are launched for certain purpose. Say Earth observation and say some SAR, synthetic aperture radar thing, and various other aspects, say, to communicate. So time period of satellite is given by this expression, 2 pi under root r cube by gn, which is also, you can take like this, if you can take g equal to gn by r square. This is 2 pi under root r plus h whole cube by g. And when we talk about near the Earth's surface, what will be the time period of the satellite? It will be 2 pi under root capital R cube by gn. This is given by this expression also, and you can easily find out. We have all these values equal to 2 pi. R is known, gravity is known, so it will be 84 minutes. This P here is the average density of the Earth. Artificial satellites, these are of two types. Geostationary, we also call it as parking satellite. This geostationary means, geo means Earth, stationary means stationary with respect to Earth. So as satellite which always appear to be fixed position at a definite height to an observer on Earth is called geostationary or partly satellite. So if you are here, say this is Earth, you are here and you see a satellite always at this place only. It is not moving. Why it is not moving? Because the Earth rotation about its axis, the time period of Earth rotation is exactly similar to this satellite. So the time this is rotating, this satellite is also rotating or revolving, you can say. This is revolving, Earth is rotating. So the Earth rotation is equal to the revolving time of this satellite. So it is always stationary. It looks stationary to an observer who is standing here. So height of the Earth's surface, the satellite is how much or how far from the Earth's surface? 36,000 kilometers. The radius of the orbit is this much. Time period is 24 hours because, as I said, the Earth is rotating, this is revolving, the time period are same, these are 24 hours. The orbital velocity is 3.1 km per second, the angular velocity is 2 pi by 24, which comes up to this value. And these are the satellites which revolve around the Sun in equatorial orbits. In the equatorial, see, it has to, if this is an equator, then it is revolving around the equatorial orbit. That is why it is stationary. The angular velocity of the satellite is same in magnitude and direction as that of angular velocity of Earth about its own axis, which I told you just now. These satellites are mostly for the communication purpose. For example, if you happen to know about INSAT 2B, INSAT 2C, these are geostationary satellites of India. Polar satellite. Now, as we just saw that the geostationary, they are moving on an equatorial orbit like this. On the equatorial orbit. The polar satellite, on the other hand, if these are the poles, they will move around like this way. So these are those satellites which revolve in the polar orbits, not on the equatorial. So the polar orbit is that orbit whose angle of inclination with equatorial plane of Earth is 90 degrees. That is, this is the Earth diameter plane, or you can say the equatorial plane. Then this polar orbit, will have inclination of 90 degrees. The height from the Earth's surface in this case, say around 880 kilometers, time period is 84 minutes, orbital velocity in this case is 8 km per second, and this depends on the various satellite. Okay, this is not fixed. If you take some satellite, it may be different. The angular velocity becomes 2 pi by 84, which is this number. We have just converted it into the radian. So these satellites, they revolve around Earth in the polar orbit, or you can say near polar orbit. These satellites are used for various purposes like Earth observation, natural resources observation, forecasting weather, studying the upper region of the atmosphere, say in geometric or GIS mapping. Polar Satellite Launch Vehicle, PSLV. These are the series of vehicles which are launching the satellites, which are polar satellites of India. Then we have orbital velocity. Orbital velocity of a satellite is that minimum. See, this is a minimum velocity required to the satellite into a given orbit around Earth. So some velocity is needed in order for the satellite to orbit around the Earth. So this is the orbital velocity. Orbital velocity of satellite can be given by, this is VO, V sub O, this is orbital velocity, is given by under root Gm by R, where this M is the mass of the planet, R is the, if you have one more relationship, you can use this capital R by under root G by R plus H. Capital M is the mass of the planet, R is the radius of the planet, and this H is the height of the satellite from planet surface. If satellite is revolving near the Earth's surface, then you can just ignore this H, so it will be R. This small r can be taken as capital R. Now the orbital velocity will become what? It will be, if you see this expression, it is going to be under root g into r only. Okay. So this is going to be 7.92 km per hour because we know the gravity, we know the radius of the Earth. If v is the speed of satellite in its orbit, VO, that is V sub O, is the required orbital velocity to move in the orbit. This is the required orbital velocity, V may be the speed of the satellite. So there is a relationship between this V and VO. If V, that is the speed of the satellite in its orbit, is less than VO, the satellite will move on a parabolic path, and of course the satellite is going to fall back to the Earth. If V equal to V0, the satellite will revolve in circular path or orbit around Earth. So this is the case. But if V is between the VO, that is the orbital velocity, and one more velocity is there, that is the escape velocity, the satellite shall revolve around the Earth in the elliptical orbit. So this depends on both the velocities, where it is going to take the circular path or the elliptical path. Energy of satellite in orbit. What is the total energy? Everywhere we always talk about the kinetic energy and potential energy. So we know by now that the kinetic energy is G capital M small m by 2r. Potential energy always is negative, so G capital M small m by r. When you combine them, you get minus G capital M by 2r. Binding energy. What is the binding energy? The energy which is required to remove a satellite from its orbit around the Earth, or say any planet. We will not talk about Earth again and again. It can be any planet. To infinity. This is called binding energy of the satellite. So if we have Earth, or say any planet, and we have a satellite here, so the energy which is required to remove a satellite from its orbit around that planet to infinity, it can be any place, is called binding energy of the satellite. So binding energy of the satellite of say mass m is given by, see, these two are equal, plus opposite in sign, G capital M small m by 2r. This is the first discussion of the topic gravitation. We'll be taking one more. Till then, thank you so much and take care of yourself.